Thank you very much, Hans, for the introduction and for the invitation. It's a pleasure to be here today to talk a little bit about very briefly what we do at Electricity Mass, and most importantly, talk about how data can be used to decarbonize the electricity grid the most efficiently. So the main motivation actually for working on this for me is to realize that climate change is one of the biggest challenges of our time. As you all know, climate change is caused by fossil fuels that are used mostly in the energy system. Like, the thing is really that our world is powered by these fossil fuels. And if we look at our energy system, energy is needed every time we want to add value in the world, every time we want to transform, mold something, heat something up. If we want to move from one place to another. So every time we want to add value in the world, energy is involved. And I find it quite entertaining to have the thought that, physicists are thinking about energy, but economists are talking about GDP. But the biggest challenge we have here is that these CO2 emitting fuels, fossil fuels, they represent most of our energy, hence most of the way you're creating value to the world. And we need to get this to zero by 2050 if we want to reach the 2-degree target. Which means, in a nutshell, we need to reinvent the way we live and add value across the world, which is, for me, an immensely exciting challenge. So the goal here is to, of course, electrify all this energy usage, but we have to remember it needs to be electrified with clean energy. So the largest decarbonization opportunity is at stake. And why is it at stake? It's simply because the way we're currently electrifying is a lot with wind and solar. And wind and solar is an intermittent energy source, which means that if we don't account for the footprint of electricity accurately, we might end up electrifying without decarbonizing. And that is really something that is worrying me. If we look at the whole hydrogen opportunity, for example, we won't be gaining much if we actually end up electrolyzing hydrogen that can be used in the heavy industry. If it's electrolyzed with fossil fuel-based electricity. So the question of accounting for the footprint of electricity is absolutely critical here. There is one opportunity, which is the availability of granular electricity data. We have built electricity maps since 2016. It's quite a popular app. It's used by many people, but in a nutshell, it tells you where electricity comes from. And this availability of granular grid data is an opportunity for us to account for electricity in a granular way and in a way that drives grid decarbonization. The challenge here is that it is tricky to actually define what the carbon footprint of something is. And I'm starting with an example outside of electricity. It's something that we all can relate to. So it is a question of what is the footprint of traveling by plane? And if we consider that question for a second, there is a first answer, which is to take the exhaust of the plane's engine, which are emitting CO2, and attributing or spreading all these emissions across all the passengers in the airplane. And so every passenger gets a share of the engine emissions, and we can distribute them evenly, which means that as a passenger of the plane, if there's 200 passengers on the plane, I get 1/200th of the plane's emissions or the engine's emissions, and that's my footprint. So that is the first answer. There is a second answer here, which is to say that the plane actually probably takes off irrespectively of what I decide to do. If I decide to stay home, there is either an empty seat in the plane or someone else actually gets to book the seat that I didn't take. So the seat will be occupied by someone else. Under that reasoning, the consequence of me not taking the plane is zero. So you could say actually the footprint, there is no change in global CO2 emissions based on me taking the plane or not. So the induced emissions are zero, so the footprint is zero. So that is a second answer here. The third answer is if everyone starts making that decision, then at some point we are reaching a critical mass where one plane will stay on the ground. So imagine the first person says, I'm not taking the plane, nothing happens. But as 2 people, 3 people, and if there's like 200 people that are saying we're not taking the plane, then maybe that's enough to decommission one plane or to make sure that that plane actually doesn't allocate it to a route. And then physically we are avoiding, one plane's worth of emissions. And so here we're taking the emissions from the engine and we're going to spread them out across this critical mass of people that need to make that decision. So we have the first answer, which is sharing emissions across everyone. The second one, which is really the immediate consequence of what I'm doing. And the third one, which is looking at the critical mass that is required before physically we're reducing emissions. And what is interesting here is that these are answers to different questions, actually. The first question is, what is my share of the plane's emissions? The second question is, what is the immediate impact of my decision? So 0 in this case. And the second piece is, what is the expected long-term impact of my decision? And there is a hypothesis underneath that, which is multiple people are following the same reasoning and therefore also making that, that decision. These different questions give us some different accounting paradigms. The first one we call attributional accounting. Attribution because we're attributing emissions to different passengers. We also call them average emissions here because it's actually the average of the emissions of the plane. The second piece is consequential accounting because it's the consequences of me doing something. And then the third one is consequential, but it's looking at the long-term marginal emissions. So the long-term effects here. So if we have to, if we go a bit further here, what we see is that the first answer is providing us with a proper incentive when making decisions. If I have to decide whether I should take the plane or the train, we all agree that in the longer run, we need a society where we have less fossil fuels consumed. So therefore, we need modes of transportation that can consume less fossil fuels. Therefore, the train is better. The first answer will properly represent that. The second answer, by giving us a footprint of 0, will basically say it's the same thing if you take the plane of the train. Doesn't have an impact. And it is physically correct. Like it doesn't have an impact immediately, but it is the wrong incentive. And the third one, though, is also giving us the proper incentive because as soon as we reach critical mass, then answer 3 and answer 1 actually start getting a bit closer together. We're sharing the emissions across a critical mass or across the passengers in the plane. A second interesting component here is the calculation complexity. The first one is very simple to calculate. It's the division of the emissions from the plane divided by the number of people in it. The second one is a little bit trickier because there are edge cases here. The thing is, if you are the first passenger that decides to not take the plane, then the footprint is 0. But at some point, if multiple people make the same decision, there is a tipping point. And it is very difficult to detect the tipping point. So imagine like the first person says, I don't take the plane. The second one does the same, the third one, and there is a certain number, the critical mass. And as soon as you reach the critical mass, then the decision of that particular person, the last one, will be the one responsible for decommissioning the plane. And so we need to identify that person and tell everyone else it's a 0 footprint, except for that last person who gets the footprint of the, or gets the footprint of all avoided emissions. So it's very difficult to actually figure out who is the person who's responsible for the tipping point. Answer 3 is also difficult to calculate, but it's because you still need to calculate the critical mass, but you don't need to identify exactly who it is. You just need to identify how many people we need to trigger this change. So we see that this trade-offs here. It's not all black and white. So we end up with those 2 accounting paradigms if we generalize for a second. We have one which is called attributional accounting. So we're making each party responsible for a share of the emissions. So we're chunking up all these emissions from the plane, giving each piece to a passenger, and then incentivizing each one of them to reduce their share to 0, and incentivizing in the sense of if you want to reduce your footprint, you will be incentivized to reduce your share of the emissions that got attributed to you to 0. Something to note here is that there are several attribution rules that are possible. We could decide to distribute emissions by passenger. We could also decide to do it by ticket price. Someone who's buying an expensive ticket is maybe more responsible for the emissions. We could even, controversial, but we could do it by weight. Like if you are contributing to a heavier aircraft, then you are contributing to more emissions. So we could say that we are going to weight the distribution of the emissions and bias them towards people who are, for example, taking more luggage with them. So this is the attributional accounting piece. On the consequential accounting, we're comparing here the decision of me taking the plane with what we call a counterfactual. So it's an alternative world where I didn't take the plane. And then we're calculating the difference between both of them, and we're assigning the difference. So what you see here on this graph is that you have a decision point, and you are looking at a realized trajectory in the future. So those are the emissions of the plane, you know, during the takeoff and so on, and it's the realized emissions. And then there is a counterfactual here in a dashed dotted line, which is what would have happened if I hadn't taken the plane. The interesting thing to notice here is that it's very sensitive to which timescale you're considering. If you only look at the immediate impact, well, it's 0. But if you look at the, you know, long repeated impact, if there's multiple people making the same decision and so on, then you end up having a different answer here. And the second piece is that it requires simulating a counterfactual. So it requires simulating this parallel world, which is something that is inherently prone to assumptions. So these are the two accounting paradigms. And so if we summarize a little bit what we just said on the plane, we look at the attributional methodology, where we're spreading out the emissions to everyone on the plane. Does it send the right incentive? Yes. Is it simple to calculate? Yes. On the consequential, on the short term, does it send the right incentive? Unfortunately, it overlooks these long-term consequences. And is it simple to calculate? Not exactly. It's quite of a tricky topic here. And on the long-term consequential, it is sending the right incentive. It's also a bit difficult to calculate. So this is why, every time that we're looking at the footprint of a product, we are typically looking at attributional accounting, because it is the simplest thing to do and to attribute, and it is a little bit non-controversial in the way that it's sending incentives. I will now switch over to the much thornier topic of looking at electricity emissions. So if we imagine for a second that we are pondering the question of what is the footprint of charging my electric vehicle at noon in California? And the thing is, a little bit like the plane, it's complicated. It depends exactly on what question you're asking and sort of what paradigm you're taking. So on the left side of the diagram, we have this attributional mindset. And under the attributional mindset, we have 3 different attributional rules that at least I have identified so far. I'm going to go through them in a little bit. And we also have the consequential world, where we can look at the short run marginal, and we can also look at the long run marginal. So we're going to go a little bit through some of these. So when we look at attributional rules here, a little bit like the plane, the electricity grid is a shared asset. So we are looking at an electricity grid where emissions are not emitted by consumers, they're emitted by the generators on the grid. So the generators on the grid are exactly like the engine of the plane. We have this shared asset, which is the grid, which is the plane itself, and then we have consumers or passengers. And there's many different ways to take all these emissions from the generators and attribute it to the consumers. So what I argue as the most intuitive way to do this is the location-based method. So basically what we're saying here is intuitively, the cable that is going into my house is connected to a junction on the electricity grid, which is also giving electricity to my neighbors. So my neighbor and me are getting exactly the same electricity. So consumers in the end can't really choose the origin of their electricity, because they can't just go to a different cable. And when we're injecting electricity onto the grid as a generator, it just mixes into the grid. And so what we're looking at here is that the footprint depends on where you are situated on the grid, hence why it's called location-based. And it is also depending on the time at which you're consuming electricity, because if you consume electricity at a time where the wind is blowing, that's quite different than if you're consuming it at a time where the wind is not blowing. So the impact of this attribution rule is that it incentivizes flexibility, because the footprint varies over time. So, you have an incentive to move your consumption to the time at which the electricity is green. It incentivizes what I call optimal sitting. So making sure that you are moving your factory or placing your factory at the place of the grid which can provide the cleanest electricity. Unfortunately, there are some negative sides to this attributional rule, which is that you have no way to fund capacity investments. So you have no way to say, I actually would like to express my preference as a consumer for green electricity, and therefore I want to be able to fund renewable electricity projects. Like, you get no credits for it under that scheme. Same with storage. Like, we know that if we want to operate a world on wind and solar, we are going to need storage for the times where there's no wind and no solar. So here there's no way to fund it. However, the last piece is that it is a credible traceability instrument. What I mean by traceability here is, if you know, I am going out on the street and telling someone my electricity is 60% green, then the intuitive way they will think about it will probably be around location based. So it is a intuitive traceability instrument in that sense. If we go to the second one in the middle of the diagram here, we're looking at market-based. So there is a instrument that has been introduced, which is called guarantees of origin, renewable energy certificates or credits. They are all certificates that represent the fact that as a consumer, I can buy a certificate from a generator, and then that certificate actually represents the origin of my electricity. So it's an energy attribution certificate. And this certificate will enable me to claim that my electricity is green. The thing is, the trade of these certificates is currently not restricted in time or in space, which means that right now, as a company, I could be claiming that I'm powered by green electricity if I bought a certificate that corresponds to a generator that produced electricity 2 days ago, or in a different grid than the one I'm connected to. And these two aspects have two consequences, which are that they don't incentivize flexibility. I have no incentive to consume electricity at a different time. And the same with the optimal setting. I can just keep my factory in my current position because it doesn't really change emissions there. However, something very important here is that it actually funds capacity projects if the purchase is what we call additional. So in a nutshell, what we're saying here is that this certificate needs to drive sufficient revenue to the project builder, such that this project actually finds place because of the investment that I did. If the certificate, for example, is too cheap, it's one of many examples, but if it's too cheap, then it probably will not contribute significantly to a new project being built. So it only funds really these capacity projects if the purchase is what we call additional. There is also no way to fund any storage investment here. And a bit provocatively, I said that the traceability instrument is not credible, in a sense that if you say that I'm solar powered during the day, during the night, sorry, that will not really be credible, because you can buy solar instruments and claim them for consumption during the night. And that's really a problem we have here. Then we have this new paradigm coming up called 24/7. It's the same as market-based, but suddenly we're adding a new requirement that these certificates need to be physically deliverable. So what we're saying is that when you're consuming electricity at a different place, at a specific time and a specific place, the certificates need to correspond to electricity that needs to be produced and physically deliverable to that space. So same hour or same 15 minutes and same location. And then suddenly here we're having a little bit of the best of both worlds. So I find that interesting. So in a nutshell, we have these three paradigms on how we can attribute emissions. They all have different consequences. If we look at the other side of the branch here, we go now to the right side, which is the consequential accounting. So remember now here, we're looking at the consequence of actions taken on the grid. So here, to map out a little bit the different aspects we're looking at, there are different timescales we have to consider. So if we look at the seconds timescale, if I decide to turn on my light bulb right now, I am probably not going to cause any power plant to ramp up or down. It's probably just the inertia of the system, which will cause a slight change of the system's frequency, but it will be almost imperceptible. It will just increase a little bit the wear and tear on various devices. And so almost no carbon impact and almost no incentive, you could say. The footprint would be almost zero. Well, a little bit back to the plane example where it doesn't really change anything. If we start looking at minutes or hours, so if you sustain the intervention for a bit longer, or if it's large enough, then the consequence happens on a minutes to hour level. And there, the marginal power plant will be caused to ramp up or to ramp down. And so in, in a very typical sense, the gas turbine is normally the marginal power plant. And so if you are deciding right now to consume a little bit more electricity, chances are that the marginal power plant is gas, and therefore you're responsible for gas emissions. So the incentives that it will send here is to make sure that you're using electricity at the time where the margin has the lowest emissions, which in a sense will reduce immediate emissions. It will try to reduce emissions that can be saved within minutes or within hours. Now, last element of the timescale, if we're looking at years ahead, so if we look at sustained demand patterns, like, for example, a smart charging system on an electric vehicle, which will cause a fleet of vehicles to change their behavior over multiple years, these types of new behaviors might change offer demand patterns, in the sense that if all these electric vehicles are charging during peak solar at noon, then suddenly the amount of the value of an hour of solar generated during noon will change, and that might affect the business case for generation assets. If you move electricity from nighttime to daytime, some existing power plants that only operate during the night might be decommissioned, and it might motivate the installation of new solar panels during the day. So on this timescale here, we are sacrificing reduction of immediate emissions at the benefit of incentivizing long-term reductions, in the sense that we're incentivizing the right investment suddenly. And we're also incentivizing optimal sitting here. Why are we incentivizing optimal sitting? Because if you are positioning, for example, your data center in a location, and you have to decide what location that would be, ideally, you want to incentivize putting it in a place where the policy decisions will decarbonize the grid the fastest. And the long-term marginal will quantify the impact of the demand pattern causing different investments in new grids. So there is something that's a little bit counterintuitive and not super intuitive, which is to understand why these short-run marginal doesn't always incentivize these long-term reductions. And I think it bears pausing here for a second, because it is a tricky topic. So short-run marginal, like the immediate impact of me doing something, as I mentioned before, it's typically gas, and it's typically gas at all hours of the day, during the day or the night. It could be hydro in some places, but even hydro, if you really think about it, the impact, you cannot really the change of a consumption cannot induce more hydro to be stored in a reservoir. You can't cause more water to be poured into a river. You can't cause more rain to fall. So in the end, there is a way to look at this where, like, short-run marginal is almost always typically gas. The second thing as well is you can't ask the sun to shine more or the wind to blow more at specific hours. And this is why you will almost never have wind or solar on the short-run marginal. However, on the long-run marginal, you will typically have solar and wind, because if you are putting your load at sunny hours or windy hours, then you are creating the proper environment for having investments that will install more capacity during the hours where you're moving your load. So on the long-run marginal, the investments will represent the long-run marginal. You will have solar and wind. So therefore, you can see on the left graph, that is more of an illustrative example. The short-run marginal doesn't have the right incentive, because it's not going to motivate you to actually put your load during solar hours to create that incentive for the right investments to happen. So I hope this is intuitive enough, but it is a tricky topic. So trying to summarize all of the very complicated things that we've said so far, we have these 5 different methodologies that enable us to quantify what is the footprint of electricity consumed. The first one is attributional, location-based. It sends a incentive, which incentivizes flexibility, but it does not incentivize financing new capacity. However, it is simple to calculate. If we look at the yearly market-based, it incentivizes this new, funding and financing the new capacity, but it does not optimize for or incentivize flexibility, consuming at the right time, or putting your assets in the optimal locations. It's also very simple to calculate. You just look at whether or not you bought a certificate, and then you can claim a zero footprint if you have. On attribution and on 24/7, it is suddenly sending the right incentive, or you could say it's sending a compromised incentive between flexibility, financing, and optimal setting. All these three are a part of the incentive. It is more complicated to calculate because you need to have suddenly a certificate system which is granular and works on an almost real-time basis. It needs to work out every hour or every 15 minutes. If we look at the consequential part of the diagram, on short-term marginal or short-term consequential, if you really want to decarbonize the grid in the long term, it is not sending the right incentive because it would only look at decarbonizing the margin and not actually making the right investment that decarbonize all of the grid. It is tricky to calculate because it requires this counterfactual. We need to model a world where your decision wasn't made, and that is a world that is not observed. All the merit order curves are not known, so that is something that is more complicated to calculate. On the long-term marginal, it is definitely sending the right incentive, but it is also tricky to calculate because what you need to do here, if you want to calculate the impact of new investment, is that we need to simulate all of the economical actors for decades ahead and simulate how they would react to, for example, a new data center being installed in a different location. So quite a tricky one, though. So there's no silver bullet here. There's compromises, and there's compromises everywhere. And I wanted to highlight a little bit of these compromises that I've seen here. So this is by no means sort of a perfect picture. This is just me attempting to highlight a few of the compromises. So here I have been looking at the computational simplicity versus how useful the incentive actually is. And you can see here at the bottom right, if you really care about sending the best incentive possible to decarbonize the grid, consequential accounting and the long run marginal would be the perfect signal. However, it is very difficult to calculate because it requires simulating, these economical actors decades ahead of time. If you want something very simple to do, you can look at the yearly market-based. However, it will not send the best incentive because it doesn't incentivize consuming electricity at the right time. So we can map all of these out, but what I want to highlight here is mainly that this is a compromise. There's another compromise that I think is interesting to look at here, and it is whether you're looking at financing with maximum impact, or if you're looking at tracing credibly the origin of your electricity. So on one end, if you are, driving in a train, if you're traveling with a train and you want to understand what is the footprint of that train, and you want to tell your neighbor, this train travels with X% electricity, I think location-based will be the answer that is the most credible for the origin of the electricity. However, if what you're trying to do is to finance the renewable energy transition and you want to maximize your impact, maximize your bang for the buck, so to speak, then the long run marginal here will be the best option. And this is why it's a tricky topic to figure out what is the right compromise here. So I will finish this presentation with a couple of practical examples because we've been a bit theoretical so far. So I'm going to go back to the example here of saying, what is the footprint of charging my electric vehicle at noon in California? Answering the five answers here. First one, on location-based, the footprint is going to be very low because in California at noon, you have a lot of solar. So if you have a grid that's dominated by solar production, you will have a low average footprint. So on location-based, it will be low. On market-based, on the yearly market-based, it will be zero if you bought a certificate. It might be high if everyone else bought certificates, because you will get the residual mix. So you will get the mix of electricity where we have subtracted all of the renewable energy that has been bought by everyone else. So it could be high if everyone else bought the certificates. On 24/7, so that is market-based, but restricted to time and location, it will be low if you purchase a certificate, but it needs to correspond to electricity generated locally and during that hour. And same problem as market-based, it might be high if everyone else bought the solar from California at that particular hour. What is interesting here immediately is that you see that creates a price signal. If there's only a little bit of certificate that is eligible to decarbonize your electricity, then everyone might want to buy it, and that can create suddenly a higher price and higher value for this local solar certificate. So it creates the incentive to consume at that time as well, and to finance the introduction of electricity or of generation assets that can produce electricity for that particular hour. If we go to marginal on consequential accounting, no matter what time of the day you are consuming electricity, it will probably be fossil fuels that will be on the margin, so will be high. There is an exception, which is if you are curtailing solar, but curtailment is very difficult to compute and detect, because when you see solar production being lowered, you actually don't know if it's because there was a cloud that suddenly came over or if it's because of curtailment. So detecting curtailment events in grids, it's something complicated and not easy to do. So in most cases here, marginal will tell you, like the marginal signal, the data will tell you that it's high. That's a high footprint. And answer 3 on long-term marginal, you will probably have a negative footprint, because if the consequence of consuming or charging your EV at noon is probably that you will cause moving some emissions or some generation from the night to the day, because instead of charging your electric vehicle during the night, you're charging it during the day, and that might cause negative emissions, because instead of having fossil fuel during the night, you're having solar during the day. So that is a little bit on long-term marginal. A second example is, where should I install my next data center? Answer 1A, location-based. You will be incentivized to install your data center in places that will deliver low carbon electricity when you expect to use it. Quite intuitive. On market-based, there's not really an incentive that discriminates the different places where you could be installing your data center, because no matter where you place it, you can still procure certificates that can cover your electricity consumption. So you will be able to claim a small footprint, no matter where these certificates, or no matter where your data center is based. On 24/7, because now we're restricting the time and location of the certificates, you will be incentivized to position your data center in places where, either policy measures are in place that will enable delivering low carbon electricity in the future, or in places where the electricity grid is already green. So inevitably, you're creating a signal to the market that says, please decarbonize the grid as quickly as possible, because that's where I will want to put my data center. On marginal, you will be incentivized to put your data center in places where the margin is the least emitting. And so again, we will be optimizing here for decarbonizing the margin, and therefore for short-term impact, but not the longer term. And on long-term marginal, we will be incentivized to put data centers in places where this additional demand or this new generation will be met by these new low carbon investments. And so you see a little bit of pattern where this answer 3 is actually getting close to the answer 1A and 1C, location based in 24/7. They also point a little bit in the same direction. So in conclusion, we have this attributional accounting, which consists of chunking emissions of the world and attributing responsibility to each consumer. What we're basically saying here is we're chunking up the world, and each consumer gets a chunk of that and gets incentivized to reduce that chunk to 0. That's attributional accounting. Consequential is one where we're looking at the consequence of an action that we're doing. And so we need to compare 2 worlds, the world where we made a decision and the world where we didn't. There's multiple attribution rules for attributional accounting, location-based, yearly market-based, and 24/7. There's several timescales for consequential. So depending if you're looking on long-term or short-term, you can have completely different answers there. So the timescale is critical. And there is no really a silver bullet. It depends on what you want to do here, and compromises will be made. But there are a couple of recommendations I would like to make here. So for example, if you really care about traceability, if you're building an app or you're building a system where you want to showcase users, this is the electricity you are consuming, location-based or 24/7 will be the most intuitive. If you're trying to finance the renewable energy transition, or if you want to assess the impact of bigger strategic decisions, such as installing a data center, or what is the policy recommendation that makes the most sense, then long-term marginal in consequential accounting is the thing that makes the most sense. And if you don't have access to long-term marginal because it is difficult to compute, there is a fallback possible here to a prediction or projected location-based 24/7 that sort of can be directionally correct. Thank you for listening. I hope this was interesting, and I know we have a bit of time for questions now.